things though. There's like no pressure. Like, because once you start mapping, you really have to encourage that process. You have to just be like, and it's like that's where weekends are great because you just don't have to have that guilt.
All right, so we will pick up where we left off. There should be up on Canvas. I can't remember if I said this last week or not, or if I did it on Friday, but I put up practice exams. So we want to start kind of looking at those. Yeah.
The smart books on Connect. Do we need to do those?
No, they're just additional resources. If you want to look at them before we kind of start covering a chapter, I usually put them up there. But no, you don't have to do those. If we go to the Files tab, I've got those practice materials there. So you've got a couple exams and their answer keys, and then what your formula key would look like. I think this says 2019. I guess I'll rename it, but it's the same kind of formula sheet I generally use. Other than that, the date for that exam will be next Wednesday. So probably a little bit of review in class on Monday. The rest of this week we'll cover the last 3 specific types of random variables we're going to look at. Might do a little bit of have time for a little bit of review on Friday, but I probably would try to keep it to the relative to the content we'll cover this week, and maybe just kind of work through some more examples, and then that way on Monday we can kind of go back and look at some of the stuff we haven't talked about. Any other questions from you before we kind of get started today? Okay. And I should tomorrow hopefully have those first Excel assignments kind of all finished graded. Your individual assignments I kind of got through, and the connects are obviously graded, but I should be able to get through those first Excels tomorrow. So we'll be looking for those as well. Okay. So let's think about where we left off. So we're looking at these discrete random variables, specifically ones that might follow a binomial distribution. Okay. So we said if they follow a binomial distribution, we know that this equation is going to tell us what the probability is. Okay. So the probability that x is equal to 2, right? Well, 2 out of how many? We need to know the number of trials n. We need to know the probability of success in any one trial p. But from there, we can just plug in x is 2, and we should be able to do this. So let's say we want to instead do something like, what's the probability that at least 3 out of 5 individuals have a college degree, given that the probability that any one person has a college degree is 30%. So we'll identify the things that we have. We left off of this example, but my n is I've got 5 individuals. My probability of success that any one individual has a college degree is 0.3. And then here, what are we looking for? We want the probability that x is greater than or equal to 3. So I think we might have done this one in class, right? But I want to kind of reiterate this example because we're going to look at some other things similar to this. So if I want the probability x is greater than or equal to 3, what did I say I could? That's the same thing as saying. I either see exactly 3 out of 5, exactly 4, exactly. So all these outcomes are mutually exclusive. I only am going to see one of them. So I basically can say, okay, what's the probability x is equal to 3, plus the probability x is equal to 4, plus the probability x is equal to 5. I don't have to worry about subtracting any of the intersections because if they're mutually exclusive events, all those intersections are equal to 0. So then I would go through, use that binomial equation over there, plug in n is 5, p is 0.3, and then use it 3 different times, right? For 3 different x values. And when I use it, come up with each one of those probabilities, simply add them all up. So the other way was, so we could have done is think about 1 minus the complement. Here it didn't save us any work because we still would have had to use that binomial equation 3 times, right? But in some situations, it might help us. So let's remember that complement rule as we work through some of our examples today, okay? Especially when we move on to the Poisson distribution. Okay? So we plug all these in, right? And come up with the 3 different probabilities, and then we just add them all up and get our, what we're interested in. And so I think this is kind of where we left off, but I want to just kind of go through it. So I also, I might have brought this up, right? Where I said, okay, if instead of 5 individuals, we had 10, what's the number of expected students that would have a college degree, or people that would have a college degree out of 10? If I probably one person's 0.3, 3 is probably the most likely outcome. So our mean, or remember another word we use is the expected value. We'll kind of write it E with the X kind of in these brackets. Is simply going to be what you did in your head there was you took the number of trials and you multiplied it by the probability of success in any one trial. When I use numbers like 10 or 100 as my number, my n, it makes it a little bit easier to think about. If n instead is like 23 and the probability of success is 0.17, it's a little bit harder to like visualize in my head or kind of intuitively calculate. But really all we're doing there is taking the number of trials multiplied by the probability of success in any one trial. So that gives us our mean or our expected value. What ends up being true, and like we could really go through the lengthy mathematical kind of proof here, where you would essentially find the mean, which is n times p. You would take your first value for x, subtract that mean, square it, multiply it by the probability you saw that first x outcome. Add to that, the next right, what you can actually prove is because this probability function follows that format, right? That's telling you the probability. You can actually work through the mathematical proof, and it always simplifies down to, whoops, n times p times 1 minus. It's kind of crazy, but it's just the way that it works. And like you write this out, things start canceling. And the variance of a binomial distribution will always be equal to n times p times 1 minus. And it kind of makes sense, especially with n, like if the number of trials is increasing, right, then the mean number of successes you should expect will also go up, right? If the probability hasn't changed and you just run this experiment more times, the number of successes you see should just be higher, right? So n going up increases the mean. It also makes sense that if I only have 10, let's say I'm flipping a coin, I'm only flipping it 10 times, the number of successes I can see only range from 0 to 10. But if I flip it 100 times, technically, even though the probability is relatively low for some of the values, I technically could see anywhere between 0 and 100 successes. So my range is much wider, right? Range is just a different measure of dispersion. And so that's why our variance also, as we see a higher number of trials, we also get kind of this higher variance. The standard deviation, as always, just the square root of the variance. So this should be pretty easy to calculate means and variances here. So one thing we'll use this idea of means is kind of thinking about this like these little toy examples. So I'm going to move kind of from left to right. But let's start out with a scenario where our number of trials is 5, our probability of success is 0.1. My mean number of successes there would be what? N is 5, probability of success in one trial is 0.1. So my mean, 0.5, right? 5 times 0.1 would be 0.5. So what that tells me is I can't see 0.5 as an outcome. This is a discrete random variable. What it tells me is 0 and 1 will be the most likely outcomes I see. And notice I'm saying they are the most likely, but it's not necessarily that they have the same likelihood of occurring. If I plug 5.1, then the x value of 0 into this equation, and I plug in n is 5, p is 0.1, x is equal to 1 in this equation, I will find different probabilities, right? So that mean is 0.5, but think about these higher values are what's pulling that mean a little bit further away from 0. So 0 is the most likely outcome, but the mean is 0.5 because these higher values are kind of pulling it a little bit further away from 0. So whenever you find the mean, the values to the left and right of it will be your most likely outcomes. They might have different probabilities, but they're your most likely. And then as you move away from that, right? If I'm thinking about this example where the probability of success is 0.1 and my mean is 0.5, well then what's the probability that I see 3 successes? What's further away from that mean, so not very likely. What's the probability I see 4? Further away, so even less likely. What's the probability I see 5? Even further away, so even less likely, right? So as I move away from that mean, or those 2 most likely outcomes, the probability becomes lower and lower. And that intuitively kind of makes sense, right? If I think about flipping a coin 100 times, the probability of success is 0.5. I should on average see 50 heads come up Well, then what's the probability I see 70? Not near. So what's the probability I see 80? Not way less. What's the probability I see all 100? Very, very unlikely, right? So as we move away from this mean, the probabilities fall. So this next one, I've kept the number of trials the same, but the probability of success is 0.5. So now our new mean, 5 times 0.5 is 2.5, meaning that 2 and 3 will be our most likely outcomes. And then as we move towards a number of successes in either direction from that mean, whether or not we're going higher or lower, notice the probabilities of seeing those numbers of successes are falling. And then you can do 0.9, and you basically end up with a very similar thing as we had over here, which is everything stacked on that right-hand side. As I then increase the number of trials that I'm looking at, right? So instead of 5, now I'm looking at 20. But now you can kind of notice I must have way more outcomes than I could potentially see. However, if the probability of success is relatively low, 0.2, my mean, 20 times 0.2 would be 4 here. Exactly. So now I know that 4 is going to have the highest likelihood, or the highest probability of occurring. And then as I move in either direction, the probability of seeing successes further from that mean start to go down. At some point, those probabilities become so low, I would guess these are very, very close to 0, right? If on average, I'm only going to see 4 successes, what's the probability I see 20? Really, really low. And then I just had another example. If you have the probability of 0.5, one interesting thing is that the binomial distribution actually looks like these normal distributions I briefly mentioned, right? Where it's exactly symmetric around whatever the mean is. We don't really explore that too much, but that is an interesting now. So hopefully this one will be a really easy question to ask you. So it should just hopefully be me registering that you're here today, right? So if I wanted the mean and variance, we're calling here's my mean equation. My variance equation is just n times p times 1 minus p. Right? Then using that same example, where 30% of adults have a college degree, I'm asking 5. Excuse me, the mean and variance of this binomial variable should be relatively easy for you guys to find. So I'll give you a little bit of time to work on this, and we'll kind of keep moving here. All right. If you haven't gotten an answer in, take your best guess here. I'm going to close it out. I think there's 13 of us. So make sure. All right, there we go. All right. So I want to point one thing out here, and I'll kind of show you the answer. So it should be as simple as kind of plugging that n of 5 and that probability of success of 0.3 into our equation for the variance. So it should be what, 1.5 and 1.05. Any questions on that? Now, one thing I want to point out, a good way to check yourself if you're calculating these, like on an exam or something, and make sure you don't make an easy mistake. What should be true about the mean relative to the variance for a binomial distribution? Yeah, the mean's always going to be larger, which is like kind of the opposite of most variables that we've looked at, right? But that's because if you notice, the variance is just the mean times 1 minus some value between 0 and 1. I mean, So this is always going to be a value less than 1. So when I multiply the mean by something less than 1, it just makes it smaller. So your variance should always be smaller than your mean. So a binomial distribution. This is kind of a byproduct of those functions. This is an easy way to kind of check yourself there. Anything else I want to say here? Okay. So I'm going to skip these slides. I thought I deleted them. I used to use them. I think it kind of confuses it. There are ways that you can rewrite the binomial to look more like what we were doing with just a general discrete random variable. And it works out to be the exact same thing that the formulas do us. I feel like when I go through this, I always confuse, like it confuses people more than it does help. But I guess they're in there if you want to take a look at it. But ultimately, if we write them the generic way, it always kind of simplifies down to give us exactly what those two easier equations would. So 1/6 easier formulas. It's kind of the end result. Right? So as we get closer to the exam, I don't want to waste time on things like that I don't think are really that important. Okay? So what are situations where we should be using this binomial distribution? So we kind of said it's when we have a success failure, the probability of success in any one trial is the same. So we can think about these different situations and which one would we not use the binomial. So let's say I want to calculate the expected number of coin flips that go up heads and 123 flips. Well, I've got a number of trials. The probability of success in any one trial is the same. So I could find, the mean or probability that out of 123 flips. So this is a perfect, we've used the coin flip example already. So hopefully we know this is a perfect example we can use the binomial. What about calculating that 5 out of 20 patients get nauseous from the antibiotic? Well, as long as there's no differences in individual responses to this antibiotic, like certain people are more or less likely, as long as it's the same across everyone, we've got a success or a failure. The success in a weird way here is that someone gets nauseous from this drug. We've got a number of trials, 20, and we want to find the probability of X being 5 or lower. This is for sure a situation where we can use that binomial distribution. What about the probability the air traffic controller at the Muncie airport makes 3 errors this week? Well, we've got kind of the probability that in any one landing, maybe he makes an error, or he or she makes an error. But what's my number of trials? I don't have any information about, the number of landings. I've only got this time period, per week. So if I can't put a cap on this on the number of trials, I can't use the binomial distribution. The binomial is this number of successes out of a number of trials. Anytime I have kind of this time frame, we're going to actually use a different distribution, which we'll talk about here in a little bit. Okay? So then we know that's the one that we wouldn't use. So this one, what's the probability that out of 5 customers, exactly 3 make a purchase? Well, I looked at historical data and I had the probability that once someone steps into the store, historically the probability to make a purchase is, whatever it is, I can use that probability. And I have probably success or failure being that they purchase something. So that would be that traffic controller one. So we'll talk about that here in a little bit. I'm going to show you how you do this in Excel. Obviously, because we're taking an exam in class, this doesn't help you too much, but this was the kind of latter half of that Excel assignment, the second one. So I'll show you how to do this. It's really pretty easy. There's one little tricky part about it. So we won't be in Excel for too long. And I'll use this, I still have the Detroit. Yeah, I like this example. I don't know why, but we'll use it. So I'm going to open up Excel here and just kind of walk you through it. Oops. So we're going to blow this up. Okay. So in Excel, there is this function called binom.dist. Okay. So basically, this function has the equation for the binomial distribution that's up here on the board, has it stored into Excel. So all you have to do is, just like by hand, you always just need 3 things: N, P, and X, the number of successes you're interested in. So the order in which you enter these into Excel, if you ask me, is a little bit, I always say N, X, and P, and here it's going to be what? X, N, and P. So it's a little bit backwards, but that's okay. All right. It kind of reminds you what order needs to be. The first thing you're going to tell it is the number of successes you're interested in finding. So I think in my example, I had what? 100 houses with mortgages on them, 4.7 foreclosed, and maybe I want to find the probability of exactly 5. So I'm interested in that out of 100 homes, 5 of them are foreclosed. So, comma, the second thing I tell it is the number of trials, which was 100 homes. I'm interested in finding the probability of exactly 5. The third thing, comma, that I'll tell it is the probability of success on any one trial. Well, here it's a success is that if I choose a home at random with a mortgage that it ends up being foreclosed in Detroit, the probability of success or the probability that a home was foreclosed, any one that I select was 0.047, 4.7%. The fourth thing that will tell Excel, right, is basically going to be kind of like a switch, right? So if I put in a 1 here, it's going to make it cumulative. So it's going to find the probability of 5 plus the probability of 4 plus the probability of 3 plus the probability of 2 plus the probability of 1. If I put in a 0 here, it's going to tell me that probability mass function value, or exactly the probability of seeing exactly 5 successes. Okay. So that last thing, let me see if I can get this, there we go, is basically if I put a 1, it switches on and tells Excel, okay, make it cumulative. If I put a 0 in there, it doesn't switch anything on, it just uses that probability mass function equation one time, finding you the probability of exactly whatever number of successes you've told it. Okay. Any questions on that? Yeah. I'll show you in just a second. So let's say I do this. The probability out of these 100 homes that I see exactly 5 foreclosed is 0.17. Let's say instead, so actually let me label this here. Let's say instead I wanted the probability X is less than or equal to, I don't know, we'll do 10. I can't remember what values in the slides. So this would be out of these 100 homes, what's the probability that at least, at most 10 of them are going to be foreclosed. So 10 or 9 or 8 or 7 all the way down to 0. Well, if I use that binomial.dist, I'll set the number of successes to be like the highest number of successes in this range that I want, right? So here I want anything 10 or below. So I'll tell it 10, comma, the number of trials is still 100. The probability of success is still that 0.047. And now I want it to be cumulative, right? So I put a 1. So what this will do is Excel will find the probability X is equal to 10 plus the probability X is equal to 9 all the way down to 0. Okay. Now this kind of makes sense, right? Like the number, the mean here, 0.047 times 100, right? The number of trials times the probability of success. So on average, 4.7. So 4 and 5 are our most likely outcomes. And then as we move from that point, the probabilities decrease. So really 10 and below, I'm capturing all of my most likely outcomes, right? I'm only, anything past 10, the probability is so small. Notice that the probability that's 10 or lower is almost 1, right? Not quite, right? But pretty close. Okay. And, if I'm trying to figure out, do I have enough people at the bank to handle these foreclosures? Or if I'm worried about, if it goes above 10, I'm not sure we can recover from this. This should be reassuring. Okay, well, not very likely that it goes over 10, right? What if I wanted the probability that X is greater than, well, I'll use 6 here, 6. Right? So maybe I'm really worried about, if it gets above 6, I'm going to be in a tough spot. So what's the probability to be above 6? How could I do that in Excel? So cumulative, right? What's the X value and goes down? But now I want to go up. So what do I do? So if this is, so if this is my event A, I can find that by 1 minus its complement. Well, what would the complement of being greater than 6 be? Less than or equal to 6. Well, that cumulative binomial distribution can tell me that, right? So binomial.dist, I want 6, the probability of being 6 or below, out of 100, probability of success is still that, whoops, 0.047. And then I'm going to make it cumulative. So this binomial distribution function will find the probability that it's 6 or below, and then subtract that from 1, which would give me the probability that it's greater than 6. Okay. Any questions on that one? So here's where it's a little bit tricky sometimes. What if I wanted the probability that it's greater than or equal to 6? Well, I can still use that 1 minus, but now, what number of successes should I be telling Excel? If I tell it 6, then that's actually going to be taking out the probability being 6 plus 5 plus 4 plus 3 plus 2 plus 1. But I want to include 6 in that outcome. Right? So I actually, what's the complement of being greater than or equal to 6? Being less than 6. But if I tell the function 6, it starts at 6. So what would I want to do? It's discrete. So yeah, being less than 6, the very first outcome would be 5. Right? Out of 100, same probability of success of 0.047. And I'll make it, whoops, forgot my comma, make it cumulative. So this will find the probability of being 5 or lower, being equal to, less than or equal to 5. Subtract it from 1 will give me the probability of being greater than or equal to 6. So it's a little bit tricky, right? When I'm using that complement rule, I have to remember with these equalities, it's discrete, so it like jumps down to the next lowest value. Okay. Now, nice way to do this in practice. Is enter your values in here. And then like, I could just play around with my number of successes is 5, comma, number of trials 100, comma, number or probability of successes here. And if I want to find exactly the probability of a specific value, I could do this. Now I can play around with, okay, what's the probability of 6? Which updates it. What about 2? Right? And I could kind of, well, okay, what if I'm looking at 200 homes, right? And it automatically kind of updates everything there. Right? So that's kind of nice. The other thing I wanted to, are there any questions up to this point? Yeah. At 1:30, I do want to do a little bit with a Poisson today. I think I'll show you this because I think it's interesting. So using this idea, there's actually one way we could, so let's go back to 100. Let's say I do something like this, right? If I start entering in like, maybe I want to go through all the way from 0 all the way up to 100. If I right click and drag down here, then you go to fill series, it always defaults to just adding 1. Okay, so I'm gonna keep doing this. Okay, I'm getting close. Right click, drag it down. All right, so the last possible outcome I can see is 100, right? So I've got this column of every possible X value. What I could then do is use that binomial.dist function, right? Where the number of successes I have right here, comma, here's my number of trials, comma, here's my probability of success. And I want to find exactly that value. When I copy this down, I want to find the probability of different numbers of successes, but my number of trials and my probability of success haven't changed for any one trial. So I'm going to freeze those cells, right? F4, Command T on a Mac. Okay. Now, just like with data, if I double left click here, when I get this bolded plus sign, it goes all the way down to where the last value is entered. So notice it goes all the way down to that 100. So here's all the probabilities. Now note e to the negative means move the decimal, what? 56 places to the left. So these are all essentially 0. Anytime you see e to the negative, value, you're basically talking about a probability that's so close to 0 that we can't even really display it with 5 decimals, right? And then you can kind of see, here's the probability of seeing different outcomes. And it kind of proves to you like, okay, the average here, 100 trials, probably success is 0.047. N times P would be 4.7. So 4 and 5 should be the most likely outcomes. Sure enough, these have the highest probabilities. Then as I move in either direction, the probabilities are falling. Okay? So kind of a nice visual of showing us that. Okay? Any questions on this? All right. Let's try something here real quick. All right, I think we'll leave it at that. We'll leave it at that for today for Excel. So that's our binomial, and I kind of have those equations there in the lecture slides as well. The next type of distribution, yeah.
If we're doing an interval, does that just mean we do two separate binomials?
Yeah, so you would, yeah, you could, right? You're just basically using that binomial to find, like, let's say I wanted to be between 10 and 20, right? I could use it once, plug in 10, that gives me the probability being 10 or lower. The other one gives me a probability being 20 or lower. I use the binomial, plug in 20. Well, then the difference between the two, that's just the outcomes that are in between. Now, we have to be careful with the equalities there, right? To make sure that whatever we're subtracting out isn't actually something we want in the interval, right? If I said, what's the probability it's less than 20, but greater than 10 or something, then I have to be a little bit careful, right? Because I wouldn't want to put 20 and I'd put 19 in, because less than 20, the first outcome that would fit that criteria would be 19. Yeah. Okay. So discrete random variable of the binomial is when we have a number of trials. I kind of showed you an example when I had those possible scenarios where we have a time frame or an interval. Right? Anytime that's the situation, we can still be interested in the number of successes, right? But it's going to be over some time or some space. Right? So generally for us, I'm going to use time examples. I'll show you a few today that are not time, but on the exam, I'm only going to use time examples, right? But we can do this over like a mile, right? We can do it over any interval. It doesn't have to be time. But for the most part, most of the examples you would want usually are going to be time. Okay? So we're still interested in, right? If we have that over any equally sized interval, the probability is the same. So if I'm looking at a week, it doesn't matter which week it is, kind of the distribution of when these successes happen is the same every week, right? So if I'm looking at a week-long interval, the probability I see, I don't know, 5 successes, whatever those are going to be exactly the same. These intervals, we think about them not overlapping. I'm never going to try to trip you up, but we do have to make sure they're not overlapping. In general, the example I'm giving you, that will be the case, right? So over this interval, what's the probability that we see a certain number of successes occur, right? So call that random variable, the number of successes X. So just like with a binomial, we have a distribution function for the Poisson, probability mass function. It looks something like this. So we're going to have to be given this lambda. So lambda is just the average number of successes we typically see over this interval. So the setup, I don't know if any of you watched the video. I put one up on YouTube. I didn't expect you to watch it, just if you want to go through it for additional help. I think I did like car crash, right? So let's say on some road, I'm interested in, on average over a week, there's 6 car crashes, right? What's the probability this week? I see 5. So on average, there's 6, that would be my lambda, my average rate that I use this. The number of crashes I see this week would be X, right? That's what I'm trying to find the probability of. The only other thing we don't know in here is this E. It's just this, it's like pi, right? That natural number pi. If you can't find it in your calculator, I mean, most even really simple calculators, it's like, it's in there and it's always like you can hit it and it automatically like puts it to the power, so E to some power, right? Now remember here when we're using it, we're always taking it to a negative power, so we make sure to put a negative sign there, but it should be on somewhere on your calculator. You usually have to hit the second button, and it's one of the secondary labels. But even if you couldn't find it, 2.71828 will always going to give to the 5th decimal is what it is. I think the way you can remember this is like something about Abraham Lincoln did something at 27. Maybe he was like, I don't know, his first political office. He was born in 1828, and like that's how you can remember the first five. But actually, in fact, there's some way you can memorize like Abraham Lincoln facts, like 25 decimals or something. I don't know. Someone told me it once and I forgot. But you could memorize it out too far if you want. But out to the fifth decimal should be fine. This one I honestly think is easier than our binomial. And we still have a factorial, so that's going to present us some issues, right? But we can still go ahead and so imagine like because we have that factorial in the denominator, what are going to be situations where it becomes really hard for me to use the Poisson distribution? When average rates are relatively high, because if I want to find the probability of say 100 successes, I can't use my calculator for sure, right? I'm going to need some larger computing power, 100 factorial in my computer, and there's nothing that I can cancel out up here. So I'm kind of stuck with the Poisson. So usually the Poisson is going to be when we have lower rates. Examples that we can use, we have lower rates, so lambda is going to be relatively lower. A lot of these examples. So the first example, kind of the age-old example of the Poisson distribution, was this guy, something, Ladislaus von Ortewitz. That was probably pretty close. Wrote this book, which actually was very critical in mathematics, but he realized that on average, Prussian cavalry or German cavalry were getting killed, kicked to death by horses, right? At an average rate of 0.6 soldiers every year. So over this interval of a year, on average, a little more than half a person was getting killed by. So what this really means is that some years in the past there was like 1 or 2, most years there was 0, right? But the average rate over a year is 0.61. So if I'm trying to project, and he wasn't thinking about this, but this is a good thing if someone's like dying. If I'm maybe liable for this, maybe the government was trying to say, how much money are we going to have to pay out, right, to whoever ends up, potentially getting killed by a horse this year? I can find the probability that no one's killed by a horse, or probably 1 soldier, 2 soldiers, 3, right? I can kind of go through and find all these probabilities because I have lambda. I have the average rate over a year. The only other thing I need is, well, what do I want to find the probability of? The probability x is equal to 0. The probability x is equal to 1, right? 0 people would kill, 1 person would kill, so on and so forth. So this is kind of the setup he has. So maybe I said, okay, well, look, usually it's on average 0.6, but what's the probability of a weird year and 3 soldiers get killed, right? But exactly 3. We've got lambda, we've got x, right? 0.61 and 3. From here, it's just a matter of plugging in our values, right? Plug in lambda, plug in our x. Should be pretty simple kind of once we have this. Okay? Now it's just a matter of using our calculators. Okay? So notice with the Poisson, the drop off is fast, especially when you have a low lambda, right? On average, we see 0.6. The probability we see 3 this year is already down to 0.02. Right? So it falls off a little bit more rapidly than the binomial does in terms of the probabilities. As you move away from that average, the probabilities take a little bit more than that. Any questions on this? I don't think this should be terribly tough. Like I said, this is almost easier than the binomial. I ran you guys about the clocks. Okay, I'll do that now because I always have to get out of the way. But I hate if you ever get asked on a survey response, and this is just me being spiteful, but about things that they could do better in the business college or anything like that. Like back in the day when I first started here, I used to tell my classes to tell them to put whiteboards in every room because I hated chalkboards. I probably pissed off some of the older professors here, but I couldn't stand it. I'd like come out of class and I'd have like just white just chalk everywhere. Tell them to move the clocks. I don't understand why they didn't put them at the back of the classroom. Because when I'm teaching, if I ever want to see where I'm at in time, I have to awkwardly do something so I can see the clock. You guys can always see the clock, so you know when class is about to be done. So like my last class starts packing up. I'm like, there's still 3 minutes left. I'm not done yet. They shouldn't be able to see the clock. I should be every room. They're right there. I don't know why. It just annoys me. So I'll stop. But if you ever get asked, write that down. Right, the clock should be in the back of the room. I got one thing done, so maybe we can get into it. So, anyways, I digress. So, what if I want to do something like this, right? I want you to do a little bit of practice here. kind of make sure that, I can look at the responses so that you guys are kind of understanding where we're at. So let's say instead we have the example, we're on average, over an hour, we see 1.25 births. What's the probability we see exactly 3 births in this next hour? This might be a very interesting example in the sense that, like, I want to make sure I'm staffed. If I had 3 births, do I have enough people on hand? So if that probability is relatively high, I might be worried. So our average rate is 1.25. What's the probability I see exactly 3 in this next hour? Remember, even if you can't find your factorial button, right? Like 10 factorial is 10 times 9 times 8, all the way down to 1. Yeah. Okay, so then we want to do for power on this one for
Oh, shoot, that's all.
oh, yeah. Excellent.
What do you get? That's what I got on my second.
Honestly, at that point, I would just use the number if it gets too tricky to use that calculator. Just 2.71828. All right. Haven't gotten an answer in. Take your best guess here. I think we got 13 of us, right? Everybody got their answer in? All right. Okay, so our lambda is 1.25. We want the probability x is equal to 3. So we know 1 and 2 will be our most likely outcomes, and then the probability kind of falls from there. So if I'm plugging in our values here, right? Lambda is 1.25, x is equal to 3. We get about 0.09. And it's kind of intuitive, like 1 and 2 are the most likely outcomes. So like we know that we're not going to see probabilities that are really high, like 0.2 or 0.3, as once we get to the value of x equal 3. But also we're not that far away from the outcomes of 1 and 2, such that the probability should be probably as low as 0.01s, right? So I mean, if I'm guessing here, probably B or D made the most sense, right? And we're not very far away from the most common outcomes. So we probably shouldn't have something as low a probability of 0.01. But we don't really know until we actually put things in. Just wanted to see you guys a little bit of practice with that. So are there any questions on this? So what if I wanted the probability of 2 or more births? So we've got an issue here, right? So if I want the probability of seeing 2 or more, so x is greater than or equal to 2, what's that the same as saying? Probability x is equal to 2, plus probability x is equal to 3. Where do I stop? The number of, women within a certain age range in that county or whatever it is, like I don't know where I stop, right? So the Poisson is left open-ended, right? Because I don't know where the number of successes stops. So if I want to find like the probability of being greater than or equal to 2, I'm going to have to use that Poisson function an infinite number of times. Well, that doesn't make sense for everyday life. So what is something else I could do? Yeah. Yeah, right. If this is event A, I know that that's the same as 1 minus the complement. The complement here would be less than 2, but the only outcomes that are less than 2 would be what? So probability x is equal to 1 plus the probability x is equal to 0. So now I only have to use that equation twice. Okay. And same kind of thing applies, especially with a Poisson. This gets a lot easier when we have 0. Because 0 factorial, 1 factorial, these are all 1. Anything to the 1 power is just itself. Anything to the 0 power is 1. So really, we're only, we're not dealing with near as much when we're looking at those outcomes of 0 and 1. So yes, we're using that Poisson equation twice, but in fact, some of the calculations, it's a little bit easier. Okay. Any questions on that idea? So anytime you have a Poisson, if I ask you for the probability of being greater than a certain value, you're not going to be able to solve it unless you use the complement. I mean, you guess you could get close, right? In this situation, if I had the probability x is equal to 2 plus the probability is equal to 3, 4, 5, 6, 7, 8, 9, and 10. Well, then the probability starts getting so low that I'm probably like to the 5th decimal at the same, same value. But really, you wouldn't have precisely the exact value. The only way you can do that is if you use this complement. So if we do that, right, we're going to add those 2 up, subtract it from 1, we move out 0.35. Okay. And this kind of makes sense because the probability that x is greater than or equal to 2, well, with a mean of 1.25, most likely outcomes would be 1 and 2. So this is going to include one of the most likely outcomes, right? But then as we move further and further from that mean, it becomes smaller and smaller probability. So it shouldn't be like the largest probability in the world, but it also shouldn't be kind of the smallest either. Right? So about 0.3 kind of makes intuitive sense as well. So kind of like with a binomial, we can think about really with a Poisson, the only changes in the distribution are coming from the average rate or lambda. So when lambda is relatively low, right, we get kind of this really left skewed distribution. And as lambda increases, it becomes less and less of this kind of, sorry, I said left skewed, right skewed distribution. It becomes less and less right skewed, right? We kind of have this like not quite as long of a right tail. I mean, theoretically, the tail always goes to infinity here, but as you get a higher lambda, at least the bulk of the probability is moving, more and more to the right. Oh, I also want to point out. So if we look at the mean, right, of 0.1, 0 and 1 are still the most likely outcomes. But if we had a lambda as low as 0.1, I mean, even though they're the most likely, 0 is way more likely than seeing one, right? But they're still the most likely, the 2 highest probability. Same thing, if it's 0.5, 0 and 1 still have the highest likelihood of occurring. It's just now like the gap between those probabilities is near as large. You go up to 2, well, now 2 is the most likely outcome. 5 becomes the most likely outcome, right? But the values right to the left and the right of those means, right? It's not necessarily they have to be exactly the same. It's not a symmetric distribution. It's always going to be skewed right. So notice when the mean is 2, 1 is also very likely. When the mean was 5, 4 was just about had the same likelihood of occurring. And that's because this goes off to infinity. So even though the probabilities are really, really low, it's still pulling it a little bit to the right. All right, I think I'll leave it at that. We'll pick up, talk a little bit more about the Poisson distribution on Wednesday, and then start talking about the continuous distribution, which will be the only, the uniform distribution, which will be the only continuous distribution that we cover before the exam. Okay? All right, we'll see you guys on Wednesday.